Welcome back to the New Quantum Era. I'm your host, Sebastian Hassinger. This is our first episode in 2026, so Happy New Year. My guest today is Chetan Nayak, technical fellow at Microsoft and one of the central figures behind the company's efforts towards topological quantum computing. Chetan's career threads together some of the deepest ideas in condensed matter physics, topological phases of matter, non-Abelian anyons, and Majorana zero modes, with the very practical question of how to build a scalable, fault-tolerant quantum computer. I met with Chetan initially at APS, the APS Summit back in March of last year, and we've been talking about doing this episode for a while, so I'm really excited about this one. We talk about, you'll hear in the interview, we talk about how he went from studying the fractional quantum Hall effect and exotic quasi-particles, initially with his thesis advisor, Frank Wilczek at Princeton, and then eventually UCLA, and then at Microsoft, where he co-founded Station Q, which is their quantum research center at UC Santa Barbara, and started working on topological quantum computing. And that whole topic really went from a thought experiment and a bunch of theoretical speculation on a whiteboard to eventually the announcement last February of finding pretty compelling proof of actually experimentally realizing Majorana zero modes on a device of their design and manufacture, and also the launch of the Majorana 1 chip, which they're working on in their R&D labs at this point. So we get into the original proposal for the topological qubit in gallium arsenide quantum Hall devices, and then their pivots to semiconductor superconductor nanowires and now gate-based devices, and how those ideas sort of crystallize into this tetron architecture, which is what they're working on now in the Majorana 1 chip architecture. Chetan also explains why topological protection is just part of the story. They're going to be implementing surface code style error correction on top of the tetrons. And so we get into that a bit. And then we talk about some of the advantages of topological qubits, in particular, the sort of more binary style control rather than microwave-based or RF-based control, and the advantages to scaling that will provide once they get to that stage. We talk about Microsoft's roadmap, how they think about their material choices, where their focus is right now, where they think they're going to need to go in the coming years, and why they believe that their microsecond scale tetron sort of sits in a Goldilocks zone for integrating an entire utility scale quantum computer into a single dilution refrigerator. Along the way, we touch on some of the key papers that shaped this field, from early theory of non-Abelian anyons to recent device level blueprints and tetron experiments. And we close with when and how outside researchers might start to get hands-on time with their topological qubits. So I hope you enjoy. All right. Thanks for joining me, Chetan. I'm really excited about this conversation. I saw your talk at the APS Summit last March when you were sort of summarizing the work that you've been doing with Microsoft on the Majorana 1 topological qubit chip. This is a modality of qubit that we have not dug into on the podcast, so I'm super excited to get into it. But if you could start by telling me a little bit about sort of your journey to how you got to this point, that would be great.
First off, thank you very much. It's a pleasure to be here on your podcast and to have on the New Quantum Era, to have a chance to talk to you, Sebastian. I know that we've run into each other a couple of times and said it would be fun to do this, and so it's nice to have the opportunity.
I appreciate you making it happen.
Yeah, thank you. So, I'm not sure exactly where to begin, but because we can go really far back. But I can say I first heard about quantum computing when I was in graduate school. That'd probably be a good place to start. And Peter Shor came and gave some. It was shortly after his. It was actually shortly after his second big paper. So people, understand that Peter Shor revolutionized and rebooted the field of quantum computing with the discovery of his algorithm. Quantum computing goes back to the work of Feynman in the early '80s, and actually parallel work in the Soviet Union by Manin.
Right.
But Feynman was very much motivated by actually something that very much excites me to this day and is exciting for the whole field, which is that if you want to simulate the real world, if you want to simulate nature, materials, chemistry, so on, you actually can't really very effectively do it on a classical computer because the real world
nature isn't classical, damn it.
Exactly. In Feynman's colorful way of putting it. And but what Shor did is he found a potential application for a quantum computer, which is factoring numbers. That is something that is exciting even to non-scientists, right? And so that of course generated an enormous amount of excitement. But very shortly thereafter, he wrote his second revolutionary paper in the field, which is showing that error correction is possible. Because people thought right after Shor's algorithm, there was this feeling like, well, isn't a quantum computer actually kind of like an analog computer? And some of the power is coming from the fact that it's analog, and we know that analog isn't going to work, is going to have problems. So it was shortly after that second paper, the error correction paper, that he came and gave a series of lectures at the Institute for Advanced. I was a graduate student at Princeton. My PhD advisor, Frank Wilczek, was on the faculty at the Institute for Advanced Study at the time, which is the institute across town in Princeton, formerly independent of Princeton University, but it's where Einstein spent the latter part of his career. Gödel,
and von Neumann built the system sort of contemporaneous with ENIAC. It's one of the very first operating computers, and the von Neumann architecture obviously still is in our laptops and our iPhones. So
exactly. So Shor came and gave these lectures there, and that was the first that I heard really started learning about quantum computing, and completely coincidentally, completely unrelated to this, I was right around that time first learning about topological phases and non-abelian topological phases of matter, and starting to understand that. And part of my PhD thesis, the work I did with Frank Wilczek, was about actually understanding Majorana zero modes and their topological properties. What happens when you braid, when you exchange and measure them, and uncovered this kind of rich mathematical structure, which in modern language we would say that, as you take Majorana zero modes, if you take topological defects, these particle-like excitations in a emergent state of matter, that as you start braiding these things around, you start doing essentially the Clifford gates. We didn't have that language at the time,
right?
But because we weren't thinking in terms of quantum computing, but we were actually working with exactly the kind of unitary transformations that people look at in quantum computing. After listening to Shor's lectures, I thought, this seems like a real exciting area. I need to work on this, but I didn't connect it to what I was working on at the time.
So am I right in I think I was reading that you were working on like quantum Hall effects is where you were doing the...
That's right.
Okay.
Correct. So the quantum Hall effect is this effect that occurs when you take a two-dimensional electron gas. So basically you make a semiconductor structure where you have electrons that move in flatland. You make a quantum well so the electrons move in two dimensions, put a big perpendicular magnetic field and cool it down to very low temperatures. And what happens is there are these emergent states of matter and, these quantum Hall states. And I'll come back to this, but, around Majorana 1, we talked about discovering a new state of matter, this topological superconductor, or I should say, the real way to say it is discover and actually engineer, because we really engineered the state of matter.
Right.
But there are topological states of matter that have been known about since the discovery in the early 80s by Dan Suey, Horst Stormer, and the theory due to Laughlin, that under these very extreme conditions of low temperatures and high magnetic fields in two-dimensional, very clean two-dimensional electron gases, there are these self-organized, emergent states of quantum states of matter that have these interesting topological properties. And one of these states, and all of these states are characterized by these fractions, 1/3, 2/5. Well, there was one state had five halves that was kind of mysterious, and its properties we still don't fully understand, to be honest with you. Although our simulations and theory give us a lot of a lot of insight into it, but I would say not fully nailed down experimentally. But what we did is we took the kind of what was not really quite the leading model yet at the time, but would later become the leading model, and understood its underlying structure. And so it was in the context of the quantum Hall effect that we first started figuring out, basically the topological properties of Majorana zero modes, and which has a very rich structure. And then, as I said, I was working on this at the time, and then I was trying to learn about this other thing, not really seeing the connection between them, and then this paper of Alexei Kitaev.
Right, I was going to bring up,
that would combine these two things that I was, trying to work on at the same time, and that of course turned a light bulb on in my head.
And Kitaev was just talking. I think it was the toric code was the first paper, right? Yep. So he was just talking in mathematical terms about topologies. So he hadn't made the connection. He wasn't bringing up Majoranas or Majorana zero modes at that stage, right?
Not yet. He started to think about that a few years later. So he was in a very abstract mathematical sense. But since I was working on this thing in the quantum Hall effect, I realized that. Yes, I mean he was.
There it is.
Specific case. The toric code is a specific case, but if you generalize it, we're talking about very similar things. And then I got a phone call out of the blue from Michael Friedman, who was at Microsoft at the time, and and he basically had come to the same conclusion. He's like, well, I've been reading these papers of yours, and I'm thinking about topological quantum computing, and I think we're talking about the same thing. And, he came down and visited me. I was a professor at UCLA in the physics department at the time. He came down and visited me, and, we spent a lot of time talking, but he noticed on my, on my desk, there was a picture of Mont Blanc, which is a mountain on the border between France and Italy, which I had climbed a few years earlier. And Mike is also into mountaineering. And he said, you know what, you should come to Microsoft and let's build a quantum computer and let's climb Mount Rainier.
I've heard a number of stories of Michael Friedman's mountaineering adventures.
So that was the initial hook, and so I went to Microsoft Research first as a visiting researcher. He was in Microsoft Research at the time, so there wasn't a quantum program yet. It was just one of the things that was happening. This is the early 2000s. It was just, sort of one of the areas within, theory of computation, within the theory group, within Microsoft Research. We climbed Mount Rainier. So we climbed Mount Rainier a couple times.
That's the easy part, it turns out.
We did the easy part a couple times over the next few years. But we also kickstarted this journey that we've been on now for, 20 plus years. And I can say, what's been remarkable is, the just how much those ideas have over time gotten richer and more connected to the real physical world and to materials and then to devices and to systems. And so that's why we're talking about, Majorana 1 and quantum computing systems now, from those early days where we were really thinking of very basic conceptual ideas. Like it was the kernels of ideas about topology and states of matter and quantum computation and complexity. And, over time, we've come to this juncture where we're now thinking about, materials, right? Materials and...
Well, and in fact, wasn't that sort of the biggest initial hurdle was largely a materials search for this, the nanowire, the structure that'll actually create those Majorana zero modes, right?
Yeah, well, yes. So, that's skipping ahead in the story a little bit, right?
Okay,
yeah,
sorry.
That did become, but in the very earliest days, it was okay. We realized, okay, there's an idea here. but like which physical system? Like, yes, you want a topological phase. Kataev thought about torque code. There was the Majorana zero modes, which we threw out in the quantum Hall effect. But what's a material system, and how do you do it? It all sounds great on paper. It's like, oh, great, you take anyons and you braid them, and that's your computation. And you can draw lots of pictures, but how do you actually make something like this?
Well, in a way, it almost seems like your challenge was the reverse of the superconducting qubits that we're used to, which are based around a Josephson junction, because the junction pre-existed quantum information science, and it was there and then could be exploited, right? And you had to figure out what that technology was, the material and the design was that would actually create this set of dynamics, right?
Exactly. Or to take another example, like with trapped ions.
Yeah.
People have been doing experiments with trapped ions, the ground state exciting to the first excited state.
Keeping time with them. I mean, Dave Wineland and Chris Monroe both say basically, when they read the paper from Serac and Zoller, they were like, oh, well, I think we could do that. And then they just sort of implemented it, right? Because they had the device already.
Yep, exactly. So in our situation, you're right, it's the reverse. And part of the reason we took the reverse strategy was at a fairly early, point in time. This was, I will say, this was something that Craig Mundy, who was senior executive at Microsoft at the time, who ended up being a sponsor for the quantum program as it developed the quantum program, really insisted you need to think about the full system and you need to design around let's say a workload or a final goal, right? You guys have a great idea, but you need to think about like sort of soup to nuts would be the expression you would use. And so, from a pretty early time, we thought, okay, look, we want to do something like Shor's algorithm. And now we of course have a lot of resource estimation, so we can make these numbers very precise. We didn't have that level of precision in the early days, but we had some understanding of, look, we want to do computations with thousands of logical qubits, which probably means hundreds of thousands of physical qubits, which this tells us something about the overhead and what kind of resources we need and what kind of control architecture. I'll come to all that. So we had some understanding that, look, you're right. You can take the approach of, well, we've got these systems already and now we can just build these things with them, but that may not get you to the scale that you need for a really useful quantum computer. Or we can work backwards from, well, here's what we need, all the things we need to be at scale. And if we work backwards, what does the underlying physical system need to be? And so that was a little bit more the approach we took, which it has a very different kind of ramp up profile. And so in that context, we thought, like, okay, so we need to make a device, and we were talking about all this very abstract stuff, but we need to make an actual concrete device. And the first place we did that was actually in the quantum Hall effect. So we thought about these gallium arsenide heterostructures, gallium arsenide devices. And gallium arsenide is a semiconductor that has some industrial applications. It is where the quantum Hall effect was discovered. And nowadays it's also observed in graphene, for instance. But that's where it was discovered, and that's where this these interesting states that are hypothesized to have Majorana zero modes exist. And so we said, okay, well, let's make an actual device where, we say this is the device layout, and if you do this with the voltages and do this measurement, then this is how you do a computation. And that's a paper that Mike Friedman, Shankar Das Sharma, and I wrote, published in 2005. So we wrote it in late 2004. And it came out of conversations where we were talking to people, and they were saying, okay, look, the idea sounds great, but what are you actually going to do? Like, how are you going to make this thing? And, we wrote that paper. And that attracted a lot of interest from various experimental groups who were, who were making devices that kind of in that same general category, because they involve quantum dots and tunnel junctions and sort of the basic building blocks of semiconductor devices, of nanoscale semiconductor devices. So, with that, as we started to get all this interest, that's really when we decided, okay, now's time, we're no longer just a few people doing quantum computing within Microsoft Research Theory Group. We're actually it's actually now a program. It's actually a project. It's quantum.
Right.
We need to actually start a quantum program. That was 20 years ago. That was 2005 when we launched it. It was only about 6 of us. We founded Station Q here in Santa Barbara, and it was all people doing theory of quantum computation, and working with academic groups. We funded a bunch of academic groups that we were designing devices and proposing experiments, and the academic groups that were funded by us were trying to we devices and do these experiments, and that was quite fruitful. We learned a lot in those early days. We got to but we also within the same idea, we made a lot of detours and or not detours, not the word, but we made a lot of pivots. So we started out doing quantum Hall effect. Then the nanowire idea came out. That also in Kitaev's early work, he had some basic aspects of that idea that nanowires also could. Superconducting nanowires could also support Majorana zero modes.
And the nanowire, it's like a grown. It could actually, you're laying down layers, and you're combining like a layer of semiconducting material with a layer of superconducting material. Is that right?
Yeah, that's right. So an important point is, what is a nanowire? It's a good question. What is a nanowire? It's basically a wire or a channel within a semiconductor device. It could be grown as a wire. It could be a channel that you've patterned within a semiconductor device through gates or through etching, either way. And it's a channel which is much longer than its lateral dimensions. And its lateral dimensions typically are in the 10 to 100-ish nanometers. That's what a nanowire is. And its length can be hundreds of nanometers or microns. In the case of all the devices that we make, it's 3 or more microns long.
Right.
And so it's several microns long, tens to hundreds of nanometers in its lateral dimensions. And importantly, the lateral dimensions, the quantization of the energy levels in the lateral dimensions are such that you have only a few transverse modes, in this wire, or that you can tune the device into a density and temperature regime in which there really are only a few modes, so that it effectively quantum mechanically is like a one-dimensional wire, that there's really no or very little motion in the transverse directions. That's what a nanowire is. And you can either what are called VLS nanowires, which are grown, a vertical wire that's grown from a seed, and then you break it off and you place it onto a substrate and make a device, or you can grow, like starting with a quantum well, as we do in the quantum Hall effect, starting with flatland with a quantum well, and then some people sometimes etch down, so they just remove parts of the wafer, and then you're left with something that looks like that is quasi one-dimensional. Or what we do, which is we make our wires by putting gates on top. So just put some metallic. Well, we first put down dielectric, and then put down some patterned metal, which are called gates. And by applying voltages, you can basically you can deplete all the electron density in the two-dimensional electron gas in the 2-day or in the quantum well, except where you want it to be in the channel, and similarly make a nanowire.
Okay.
So the motion detector turns off the lights in my office if I don't move enough. So
you have to get more gesticulation then.
Yeah, exactly. so
that nanowire then the on the ends of that is where you're actually measuring the Majorana zero modes, right?
All right. So when this is superconducting, and the way to make it superconducting is to coat it with a superconductor, and it inherits the superconductivity of the superconductor. So as I said, there was this work of Kitaev, suggesting that superconducting nanowires. There was this beautiful work of Fu and Kane saying, well, look, you can use the proximity effect to induce superconductivity, and they were thinking about actually surface states on something called a topological insulator. And then there was work from the Maryland group, Dasharma, Luchin, Sao, Tiwari, that where they said, well, actually we can actually do that in a semiconductor with strong spin orbit coupling, and then further work built on that, the nanowire idea, and then there was an explosion of ideas around how to do this with nanowires. And the thing that that makes that such a great idea is implementation of this topological concept is two things. Number one, this is the double-edged sword, I suppose, but you have a lot of choices of semiconductor and a lot of choices of superconductor, right? And so
the search space is large.
Yeah, the search space is large, which means you can really tailor it to have the properties you want. So with the quantum Hall effect, one of the difficult things it was at that time, it was the early days of graphene, but at that time, one material, very hard to grow, and if you want to change some parameter a little bit to get sort of a qubit that was optimal in one way or another, there wasn't a lot of freedom, right? There weren't a lot of knobs to change. And as you think of designing a device with millions of qubits, there are things you're going to want to optimize and change, right? You care about the size of your qubit, you care about the speed at which you're doing it, you care about you ultimately are going to want to do rapid measurements and rapid operations, and so you want to be able to read out fast, and so then the RF properties.
You want to optimize everything in a qubit.
Optimize everything, right? There's so many things you want to optimize, and so the good thing is number of choices of many choices of semiconductor, many choices of superconductor, and there was and the ability to really you would think to like design the material you want. Now the flip side I'll say is there are a lot of choices of semiconductor, a lot of choices of superconductor, so it's a large search space, and so that can really lead you down the rabbit hole. And the idea of putting together a different superconductor, different semiconductor gives you a lot of freedom, and it means that you can make the semiconductor have the properties that you really want, which is large spin orbit coupling, very high mobility, so make it very clean, very tunable density. So those are things that semiconductors can be really good for. Without having to worry that much about superconductivity, because you're going to get you're going to inherit it from some superconductor, right? And you can make the superconductor optimize those properties. But then there's an integration challenge, which is, does that semiconductor that's optimal and that superconductor that you think is optimal separately, do they play well together? Can you actually grow them? Is the interface going to be good? Because you could get the best of both worlds. You get the best possible semiconductor, best possible superconductor, great. But you could also get the worst of both worlds, right? You could get all the bad properties of superconductor and all the bad properties of semiconductor, and then it's not helpful. The more different materials, the more layers you have, the more interfaces, and the more interfaces is the more places where the interface can be rough, for instance, or there can be interdiffusion between different species of the interface. So interfaces do let you get the best of both worlds, but they also bring challenges. In any case, it was a pivot, and we pivoted towards this towards this class of materials and class of device designs around it, and in that context, we thought about, okay, for this. We are based on this nanowire idea. Like, what is the architecture actually going to look like for a large-scale quantum computer? And in 2016, I guess it was published in 2017, a large group of us wrote a paper, kind of laying out. Okay, this is we had a couple of choices. This is a set of like 2 or 3 different qubit designs, and the architecture we build around that, the types of operations, a little bit about the kinds of error correcting codes we put on top of it, and that was that was sort of. In 2005, when we launched Station Q, it was based on this first kind of practical topological qubit idea, which was taking a lot of abstract ideas and making a concrete device, which people have attempted to make, and there's some interesting partial results on that from, among others, Bob Willett, who's at Bell Labs. The device in the 2017 paper. That was sort of taking a lot of these nanowire ideas and putting them together into a qubit and qubit architecture, right?
Right, an actual, like Craig Mundy's point, it's at least it's a systems architecture rather than just a physics experiment.
Rather than just the physics, exactly. That's exactly the right way to think about it. And so because we then had to also start thinking about, like, okay, how are we going to measure and manipulate these qubits and make sure that we do it fast, because we want to be able to run deep circuits. So a lot of thought went into that, and where we've been is really on a journey in some sense of making that more and more real. That was still, as concrete as it was, there were still a lot of assumptions and idealizations there, and we've been making that more and more real. We grew substantially right after that, starting around 2017. That's when we started building up labs. And, instead of working with various academic groups that we're funding, we brought a lot of work in-house so that we could have tight our collaboration and coordination between, the design of the devices, the conceptual ideas, the design of the devices, the fabrication, growth, et cetera.
I mean, that sponsored academic research, it's an enormously powerful tool, but it does tend to, once you have done the high risk, high reward sort of phase and you've gotten your results, it's a natural sort of next stage to pull in the most promising, the capabilities you need to plumb the most promising results out of that phase. So that makes total sense.
Exactly. I mean, the way that I describe it is I say, what academic research is extremely good at is exploring a lot of phase space, because you in many cases you have the freedom to explore a lot of ideas, some wild, some safe, some not so safe, right? And really kind of like do a random walk through a huge parameter space. And in an academic lab, you might have 5 or 6 different projects, and they all usually have relative, they don't overlap that much, right? By design, because different people are trying to, like the students are trying to graduate, get a postdoc, the postdocs are trying to go off and become a professor, and they need to actually differentiate themselves, right? Yeah. And have distinct projects so that they can, of course, they are somewhat constrained by they're all in the same lab and the same capabilities, but they're trying to differentiate themselves, and and you're trying to encourage them to branch out in different directions, and so you explore a lot of phase space. But if you have a roadmap, once you're at the point at which you can formulate a roadmap with a set of milestones on the roadmap and things that you have to do in a certain order, in a certain way, well, that exploration is actually not the optimal way to go down the roadmap. Yeah. You want to be much more disciplined and much more tightly coordinated. Right. And you
need to bring in some engineering discipline.
Exactly. Yeah. And so once we were at the point at which we could start to trace out and then make more concrete what the roadmap is, then of course it made sense. We started bringing a lot more things in-house. Now, the reality is, even once you have a roadmap, of course, you learn things along the way. You adjust the roadmap as you learn more things. You make pivots as necessary. And, in the very early days, we were thinking about these VLS nanowires. And, we realized that it was never going to carry us very far down our roadmap anyway. And
very challenging fabrication task. Yeah.
Exactly. Yeah. And so we knew that there was not a long-term roadmap based on that. And so there actually wasn't really that much benefit in the short term. So we made a pivot and said, look, we're going to go to these gate-defined nanowires based on 2-dimensional electron gases. And we see a roadmap heading out upon that. We made that roadmap more and more concrete. And reorganized ourselves very much more into, like you say, more of an engineering organization. Obviously we still learn new things, and we're at the cutting edge of science. So we're still making scientific discoveries and reacting to what we learn. But at the same time, we are trying to make deterministic progress along a specific path towards a quantum computer. And so I think what's unique about quantum computing is that it is very much at the cutting edge of science. Discoveries are being made of really kind of fundamental things, and at the same time, we're building a technology. But exactly. The reality is, as people were first making steam engines, they hadn't discovered entropy yet, right? So the same law of thermodynamics was formulated as steam engines were being used and built. So as the internal combustion engine was being developed. So it's not the unique time in science that you're developing the technology.
That's a good point.
The science.
I mean, the whatever Rutherford's electron beam, proving that the electron exists and measuring its mass is also the basis of the CRT and television, right? I mean, similar kind of fundamental. So that's super interesting, Chetan. I mean, there's so much I want to follow up on, but a couple of things sort of stuck in my mind. One is, so those Majorana zero modes at the ends of the wires those are quasi-particles. Those are sort of emergent behaviors out of that system that you've engineered, much like a Josephson junction creates sort of that artificial atom they talk about in transmon qubits. Does that, going back to the origins of your interest in the non-Abelian statistics and quantum Hall effect, do those quasi-particles sort of bolster the case that Majoranas are a real particle, or is that sort of orthogonal to the whether Majoranas are real or not?
Yeah, so interesting question. In some sense, the word quasi in front of particle is
does a lot of work.
It's a matter doing a lot of work. It's also a matter of taste, because the particles that we think of as particles, like the electron, the electron has a mass and a charge in this particular vacuum state of the universe, which has electroweak symmetry breaking, and, electrons would be massless in another, phase of the universe, in an early universe before electroweak symmetry breaking. So, the particles we have are emergent properties of the vacuum state that we live in, which is not the unique vacuum state, and may not be the same vacuum everywhere in the universe, and certainly not in maybe the very earliest stage of the universe. So I think, that's a little bit of a philosophical point.
It's a good one.
But but if I just restrict myself to solid state, physics, then in solids there are phases of matter, states of matter, in which you have excitations that have a particle-like nature that we call quasi-particles. And an example is if you make a solid, it has the vibrations in a solid. They're called phonons, right? They're particle-like. In some sense, they're a little bit like photons, which are the particles associated with light, but they are called phonons because they're like the particles associated with sound waves, right? The vibrational waves in a solid. If you melt the solid, you go to liquid, they go away, right? They are a factor. They are a property of the fact that the solid has this lattice structure, and you have these lattice vibrations, and the liquid doesn't have those. And so, as a particle-like excitation at zero temperature, right? So it doesn't have those, and so that's just a property of states of matter, is that the particular excitations that you have, the ways in which you can excite above that ground state, depends on what the state is, right? And the quantum Hall effect, or topological superconductor, has excitations that are very different from a metal or an insulator, right? In an insulator, like a semiconductor is a type of insulator, right? Just has a small band gap, and the excitations in a semiconductor are basically like an electron. They look very much like an electron or a hole, right? Because if you take the absence of an electron in a semiconductor, when you're sitting in the band gap and the valence band is filled and the conduction band is empty, you create a hole by plucking an electron out of the valence band. And that looks like, in some ways it looks a little bit like a positron, right? Because it has positive charge, but we call it a hole. It's an excitation of a semiconductor, but it has positive charge. And the interesting thing is, in a semiconductor like the semiconductors that we deal with, those holes can actually be can have very different properties from what an electron looks like in vacuum, right? And in fact, the electrons in the conduction band can look very different from an electron in vacuum by virtue of the fact that they're in a solid, that their magnetic moment or their G factor, which tells you how strongly they interact. They feel the spins feel a magnetic field, can be extremely different. Their spin-orbit coupling can be extremely different. Their effective mass can be extremely different. So the properties of a quasi-particle, of an electron-like excitation in a semiconductor are very different from what they look like in a vacuum. And so that's kind of the simplest example, where even though they have the charge of an electron, right, and they're fermions, so it's a fermion, it has spin a half, it has charge E, but its G factor is very different, its spin orbit coupling is very different, its effective mass is very different.
That's interesting.
So many of these properties are quite different. Do I call them? People tend to call these electrons and holes, but they are quasi-particles of some kind, right? They are excitations in that system.
It's really interesting. It's almost like you were saying. I mean, you're bringing engineering into the pursuit of the fundamentals of science, and you're engineering these devices to bring out the attributes, these statistical nature of these different behaviors that are exploitable from a computational or a technological perspective, but are also exhibiting sort of these fundamental behaviors of the universe that we've been discovering. So that's interesting. I hadn't really thought about how fuzzy the line is between fundamental particle and quasi-particle behaviors. But a lot
of our sorry, just to finish the thought, like a lot of our technologies that we have depend on mass is and so on, right? These properties. Now, in a semiconductor, those properties, like I said, the charge is still E and the spin is still a half and it's still a fermion, but lots of other parameters are different.
Right.
Other parts we're talking about have a more dramatic difference, right? Which is in a Majorana fermion, is, or a Majorana zero mode. Now you're starting to talk about particles that don't have a charge, and if you talk about a defect that supports a Majorana zero mode, you're now talking about something that's neither a fermion nor a boson. So now we're talking about more radical departures, which are
weird,
which are even weirder, and which are possible precisely because of the restricted dimension that you got quasi two-dimensional, where they live in two-dimensional plane, or like you said, at the ends of a 1D wire, that you can have these particle-like excitations, call them quasi-particles if you like, and those objects really look very different from an electron or a photon or any of the excitations that we have in our vacuum, in the vacuum of empty free space. And so, just connecting it back to the point you made, and like what this does for us from a computational perspective is, this particular one is, if we have a nanowire, okay, with Majorana zero modes at the ends, what that means is that now is it's superconducting. First of all, this is a superconducting nanowire, and superconductors very famously have this property that the electrons form pairs called Cooper pairs, and those pairs condense into a superfluid, correlated state where they all kind of condense into the ground state. And as a result, when you take mesoscopic superconducting devices, there's actually a big difference between even and odd number of electrons, because with an even number of electrons, they've all formed pairs, and they can all condense to the ground state, and everything is cool, right? And if you have an odd number, there's a energy penalty because there's some electron that didn't pair up, and they all want to pair. So if something if one electron is left frustrated, then there's an energy penalty associated with it. It's a measurable energy difference. This is something that's observable and has been observed. Now, the cool thing about topological superconductors is actually they can actually accommodate the odd electron without any concern, right? Because of the Majorana zero modes, those are places where, so everywhere else in the middle of the wire, a pair can kind of condense into the ground state, but an unpaired electron can't because it's unpaired. And condensate is made up of pairs, but the ends of the wires here, Majorana zero modes, you can actually absorb that unpaired electron, and then it just gets mixed into the condensate, and so or emit that unpaired electron and send it off. So as a result of these Majorana zero modes at the ends of the wire, a topological superconductor can accommodate an even or an odd number of electrons perfectly well. It's just as happy, and so as a result. And you can't tell, like this condensate looks the same. No local measurement can tell you the difference. So you look at the condensate and it just looks the same. And so therefore now a topological nanowire can be either even or odd number of electrons.
Right.
So that's a 0 or 1. And it's a 0 or 1 that's very well protected because nothing locally can tell you whether it's a 0 or 1.
Right. I was going to say, you just described the fault tolerance right there with the ability to accommodate. Okay. So interesting.
So that's kind of the basic idea, and what we did in that 2017 paper is we figured, okay, well, how are we going to make qubits out of it? Turns out, for technical reasons, it's actually really nice to make a qubit out of 2 of these wires rather than 1. And I can explain the technical reason, which is, with 2 wires, both wires could be odd number of electrons, or both could be an even number of electrons. That would be our 2 states, and we wouldn't deal with like one being odd and one being even. And the nice thing about that is, if your 2 basis states are odd or even, then the entire thing can have a fixed number of electrons, right? You don't have to worry about like exchanging electrons with a reservoir or anything like that.
Right.
You can have a fixed number of electrons. It can be like 10 million, let's say. And you have your two wires connected together so that you can't isolate either one from the other. And the total number of electrons is, whatever it is. But one wire can be odd and the other odd, or one can be even and the other even. And that is that basic H-like structure with these two nanowires.
The tetron.
Connection between the tetron, is what I presented at the APS meeting, and we have a paper on the archive about it from the summer, showing that we can do the Z and X measurements on it. And so pushing that idea to its logical conclusions in terms of building or designing a qubit architecture, a quantum computing architecture around it is what we started, as a project we started in 2017. A lot of the basic ideas were there. And a lot of the challenge has been, okay, now we got to make devices that have sufficient quality to enable us to do that. Because if you remember, I said, once you start making complex devices with many different material types, you always run the risk that you're going to get the worst of both worlds rather than the best of both worlds, right? And so, in this kind of situation, you have to then make a lot of choices there's a lot of decisions have to be made to make progress. Like even once you have the basic architecture, you have to decide, well, okay, what semiconductor we're going to use, because there's a lot of choices. I mean, indium arsenide is the basis of what we're using now, but there's indium antimonide, there's mercury telluride, there's lead telluride. There's a lot of different potential, semiconductor materials, each of which has nice properties. And if you point to one or the other, you can sort of, if you focus on one metric, so a different one is going to win according to any metric. There's a lot of different superconductors you could choose. So, there was a complex decision-making process there where, I said, hey, look, we need to take all these factors together, really have a rigorous decision-making process around taking, taking the different material properties, the technology readiness level, the availability of process techniques, the compatibility of materials. So there are many different criteria and many different material combinations. And we landed where we landed because of the combination of the highest score in essence, right, among these many different metrics. But we also understood that was part of that score was what can we do today, as opposed to what can we do a year from now, 2 years from now, 5 years from now. So the roadmap includes changes of material type, because we knew, okay, look, we want to make a device now, we should do this combination, but in 2 years, we want this other combination to be ready for us to be able to make devices with that, because we know that we need these extra properties as we get to more complex devices. And so our roadmap actually has, in a sense, it's moving along two axes. One axis is just device complexity, more qubits and more features and more functionality. And the other is underlying properties of the qubit, which is things like how large is the topological gap, which, remember the electrons form pairs. It's the energy cost of breaking a pair. What is the signal to noise ratio of our ability to measure out that qubit, which depends on materials properties and system properties. So, a number of different sort of quality type metrics along one axis, complexity metrics, or device functionality metrics on the other. And a roadmap takes us in a certain way through this two-dimensional space. Ultimately, we're trying to get to, utility scale, but the exact route depends on, choices that you make. So that's,
the intrinsic hardware design, the qubit design, has a degree of error protection in it, but you're intending to still implement some sort of topological code in the way that you actually program and interact with the measurement-based sort of computation. Do you have a sense at this stage, how many of these tetron qubits you'll need to have in a device to be able to implement error correction at the logical level, and also what the kind of ratio is going to be for your physical qubits to logical qubit kind of implementation?
Yes, excellent question. So the answer is yes. So we have published papers on exactly this topic, which is looking at different codes that we can use. And one of the things that's very that is really great about this particular architecture is, if you think about error correcting codes like the surface code, or there's a class of codes called Floquet-Ha codes. Floquet codes developed by Matt Hastings and Jungwon Ha, at Microsoft. Part of our team, which are also based on topological states. What either of these codes do is at the end they can be formulated as what you're really doing in a quantum computer is you're doing lots and lots of 2-qubit measurements.
Right.
You're measuring XX, ZZ, YY. You're doing lots and lots of 2-qubit measurements. You do logical gates through like lattice surgery or something like that. It's set effectively just by you skip some of those measurements. Every now and then you skip some of those measurements, and that's kind of how you do a logical gate. And then you prepare offline magic states and you inject them in, right? So it's a lot of 2-qubit measurements, a lot of magic state preparation, distillation, and then injection, magic states. So really, aside, and I'll come back to the magic state preparation, but by and large, what you're doing is 2-qubit measurements. And what's cool about the Tetron architecture is that 2 qubits are a native operation. Is
right.
that, and this is the work that's very much in progress right now, but the way we measure our qubits is we come back, if you recall, our qubit is it an even or odd number of electrons in a topological nanowire? And the way we measure that is you can't locally measure it, but we can, if you can connect the two ends, which we do through a quantum dot, then actually an electron that tunnels around a loop, every time an electron goes past another electron, it picks up a minus sign, right? That's Fermi statistics. And so when an electron goes around the loop, it counts whether you have an even or odd number of minus signs, and so it can tell you, do I have an even or odd number of electrons by going around that loop. That's a Z measurement on our qubit.
Right.
And the X measurement it's a loop that bridges the two wires. So it goes around half of one wire along a trivial backbone, and then the other half the other wire. And it's something that doesn't commute with so the order matters whether you do Z measurement first or X measurement first.
Okay.
The 2-qubit measurement is actually a very similar kind of measurement. And the way you measure this is this even or oddness gets imprinted on the quantum dot. And the quantum dot, what you do is you measure effectively its capacitance. The capacitance shifts. We measure the capacitance between a gate and the quantum dot, which we do by embedding it in an LC circuit. And we measure the change in the RF response of that circuit. So you make a small shift in the capacitance. That changes, for instance, the resonant frequency of the circuit. And we can measure that in a dispersive measurement. So sit on like kind of the shoulder of that resonance. 2-qubit measurement, actually, like if you have two of these tetrons coming in like this, there are quantum dots that you can activate that let you do a loop that connects the 2 qubits. It kind of goes around half of one qubit and then half the other qubit, either XX on neighboring or ZZ on neighboring this way, and which are the native measurements you need for these kinds of codes. And again, that turns out to leave an imprint on a quantum dot. You measure it dispersively from a capacitance shift. So a 2-qubit measurement is a native measurement for us. It doesn't involve, in many cases, it's not usually a native measurement. Usually what you have to do is you have the measurement you have is you measure in the computational basis. And if you want to measure in another basis, if you want to measure in the X basis, you do a Hadamard gate.
Right.
And measure in Z. And if you want to measure a 2-qubit gate, like you want to measure XX, well, you run some circuit so that when you measure Z on an ancilla, it's the same as measuring XX on your 2 qubits. But we don't have to do any of that. It's a native measurement. And so the native measurements for us, so that means that there's actually a lot of efficiency in how we implement these codes, because the native measurements are the measurements you need for error correction.
Right.
So having said that, long term, we've done resource estimation, and again, it depends on exactly what error rates, physical error rates we're able to hit. It depends on the exact, precision with which we're able to do these even oddness measurements, right? Right now, what we demonstrated was something like on the Z measurement was like 95%, assignment fidelity, or 1% assignment error rate. Actually a little bit better than that, 99.5 in the archive paper. So, we ultimately would want like 3-4 nines of fidelity on those measurements, which depends on a lot of things, amplifiers and, resonator Q factors and, very important engineering of the system. And so a lot depends on the exact numbers, but, at a high level, we're targeting millions of qubits.
Yeah.
We're targeting millions of qubits. and a ratio of physical to logical qubits that's in the 100 to hundreds. So, so that's what we're talking about, in the hundreds. And that's that. And so, we want to have thousands of logical qubits. So, depending on the application, we've worked out, we've estimated the resources that are needed for that application, including, the thing that I didn't discuss in much detail, which is the magic states. That you need magic state factories and distillation and injection. So, so long story short is, we have a pretty concrete target and a roadmap of what we're doing. It definitely involves quantum error correcting code, such as the surface code or Hastings-Hawk code. I think that the things that I would say that are different, because lots of people, lots of approaches do involve things like the surface code. So what are the differences? So I think the differences are that the measurements you need to do are native for us, that we just do those natively. Secondly, those measurements, remember I said that this comes about from quantum dots that are coupled to our qubits. So the basic operation you do is you just turn on and off the coupling of the quantum dots. Yeah. So it's very digital. If you remember, when we're going back to the original Peter Shor, there was this feeling like, hey, this almost sounds like analog computing.
Well, and with microwave control on most superconducting devices, it still looks pretty analog.
It looks pretty analog, right?
Yeah.
So
digital control would be great.
Yeah. So this is digital control, because what we're doing is we're doing a set of on-off, instructions, turn on or off this coupling of the quantum dot to the qubit. One of the things that enables to put a lot of that control down in the cold. So we've developed CMOS chips that operate at cryogenic temperatures, so that instead of trying to send a lot of instructions from room temperature down into to control a million qubits, because one of the things that isn't always appreciated about a quantum computer is, unlike a classical computer where you could have billions of transistors but thousands of control lines, if you have a million qubits, it's a million or order of a million control lines. Every qubit needs to
I know.
Right? And so that's the one of the real difficulties here. And because our control is on-off switches, we can generate that control down in the cold, right? It's a relatively, which is to say, we can design chips, classical chips that are sort of stripped down, that don't generate a lot of heat. The problem ordinarily of trying to put a chip in the cold is, well, A, it might not run well in the cold. It needs to run at room temperature. But B, if you try to run it in the cold, it's going to just generate a lot of heat, and you're going to cook your qubits, right?
That's right.
But for the type of control that we need, which is all these on-off switches, that is something that you can actually generate down in the cold. And so I think that's the other key difference. I would say
that's interesting. So, yeah, I hadn't thought of that. I mean, that really does give you a potential advantage for physical scalability. That the not having to stuff a wire down there for every single qubit is a huge advantage. Yeah. So okay.
And sorry, I know we're at time. So if I just hit on the two other things, which is the scale of the qubits, for the materials we've chosen and the parameter range, the scale of the qubits is like our wires are, currently we're around 3.5 microns, but, we're not going to go much longer than 5 to 10 micron long wires, So it's on the order of a few to 10 microns long. Right now in this direction, if you include all the quantum dots and the ancillary structures, it's under 10 microns. So it's, these qubits they're pretty small, but they're not extremely small. It's actually Goldilocks zone, because at that scale of 10 micron by 10 micron, you can put millions of these onto a small chip, onto a few centimeter by few centimeter chip. And so that means that, at least as far as the footprint is concerned, you don't need multiple wafers, you don't need multiple chips, they don't even need to be multiple fridges, right? So because we don't need a massive number of control lines coming into the fridge from room temperature, and because we don't need a massive amount of real estate to put millions of qubits, we can put a very large quantum computer into a single fridge with a classical controller near it. So I think the size, there is a Goldilocks regime where we are in size. Some qubits are extremely small, and so it's very hard to get all the control lines in. Some qubits are very big, so it'll have to be a multimodal system, and we're neither of those two cases. And the other thing is the operation time. What we're targeting is basic operations and measurement is operation time on the microsecond scale. Right. And microsecond is neither too slow nor too fast, because if you were much slower than a microsecond, then things like Shor's algorithm or quantum chemistry was going to take years to run. And much faster is nice from some perspectives, but it's actually also a little difficult because, in error correction, you have to do a lot of real-time feedback. You have to process all this data and then make some decisions. And if you had to go much faster, that also is a little tricky. So it's actually in kind of a sweet spot on size, speed, achievable, what we think are the achievable error rates, and then of course the digital control. So I think there are a lot of aspects to what we're doing. Since you asked about error correction, which every kind of quantum computer has some kind of error correction. I think topological quantum computers, Microsoft's quantum computer, it's not going to be something where everything is done in hardware and there's no error correction. There will definitely be what we might call conventional error correction, but the implementation is unique, and the other things that are come out of the topological character actually impact the practical engineering, the number of control lines, the footprint, the speed, and so on.
Fantastic. Well, this has been super interesting, Chetan. The last question I want to ask you is, do you have, and this may be an unfair question, do you have any sense of when people are going to be able to get their hands on a device like this to start actually, experiencing the uniqueness of this platform for themselves?
Yeah, that's a great question. And, the answer is going to be a little complicated. As I said, we've been very much focusing on doing things in-house, to have the control. We are looking at some collaborations now with external groups, academic groups, where they could either try to run some small algorithm or experiments on our devices, or maybe we even send some devices to people and they have a chance to test them. We're working with DARPA, so we're in the final stage of the DARPA US2QC program. There's 30-something companies in this program. Only two, us and one other company, have gotten to the final stage, phase C of this program. So we're actually working very closely with the U.S. government, who is getting their hands on a lot on our devices and systems. So I'd say I think we're at that stage of working closely with the U.S. government, starting to work with some academic groups in terms of when it would be sort of larger group and where you could just pull out a credit card and go on and to Azure and start using it. That's going to be a little bit further down the road, but some of these kinds of interactions are already starting to happen.
That's fantastic. Well, that's great. I really appreciate your time. This has been super, super interesting. Obviously, totally unique modality with lots of interesting engineering attributes and challenges, and also fundamental science, which is really fascinating. So I really appreciate your time, Chetan.
Awesome. Thanks a lot, Sebastian. Thank you. It was a pleasure talking to you.
Thank you for listening to another episode of the podcast, a production of the New Quantum Era, hosted by me, Sebastian Hassinger, with theme music by OCH. You can find past episodes on www.newquantumera.com or on Blue Sky at newquantumera.com. If you enjoy the podcast, please subscribe and tell your quantum curious friends to give it a listen.